We know the basic steps for drawing a Lewis structure include calculating the total number of valence electrons in the inventory, identifying the central atom, placing the outer atoms around it, and connecting each outer atom to that central one with a single bond. We then know to fill the shells of the outer elements, place any remaining electrons as non-bonding pairs on the central atom. Then once you use up all of the electrons and you have zero left over, you check the structure. So far, our goal has been when we check that central atom to make sure that it has 8 valence electrons. If it had 8, it was done. If it had less than 8, we brought it up to having a total of 8 by creating double or triple bonds. What we now need to consider is that there are exceptions. So there are cases where you're going to reach 0 electrons left over, and you're going to check that central atom, and it's not going to have 8, but it's going to be correct. The Lewis structure is going to be done. So there's 2 exceptions that when they are the central atom, they want to have less than 8. So boron wants to have 6 valence electrons when it's the central atom, whereas beryllium wants to have 4. The other type of central atom exception is what's called an expanded octet. So when you go through all of your basic steps and you're checking that central atom, you're going to see that you are forced to have either 10 or 12 electrons on that central atom. So you're just following your steps and you end up with an expanded octet. Generally, elements in periods 3 through 7 can have an expanded octet. Those elements are not always going to have an expanded octet. It's just a matter of following your rules to see that you end up having 10 or 12 electrons on that central atom. And the key thing is you're still always checking that central atom. If it has 8 valence electrons, it's following the octet rule, it's done. If it has less than 8 and it's not boron, it's not beryllium, that's when you're creating those double or triple bonds. But now if it has less than 8 and it's boron and it has 6, it's done. If it has less than 8 and it's beryllium with 4, it's done. If you check the central atom and it has 10 or 12 valence electrons, it's an expanded octet and it would be done as well. To draw the Lewis structure for xenon tetrafluoride, I'm first going to do the inventory. So there's xenon and fluorine. There's 1 xenon, 4 fluorines. Each xenon contributes 8 valence electrons, whereas each fluorine contributes 7. I multiply across and then add to get a total of 36 valence electrons. Xenon is placed as the central atom. The 4 fluorines are placed around xenon. Each fluorine is connected to xenon using a single bond. That uses up 8 valence electrons total to now give me 28 valence electrons left over. I'm now going to go through and fill the shells of the outer elements. And as I'm adding into the Lewis structure, I'm subtracting from the inventory. So I have 22 left over. Now I have 16. Now I have 10. And now I have 4 left over. So I'm going to place those 4 remaining electrons as non-bonding pairs on the central atom. So I'm going to add 2 non-bonding pairs onto xenon. I'm giving these non-bonding pairs their own real estate. I'm keeping them apart so I can clearly see that there's 2 non-bonding pairs on that central atom. Now I've used up all of my electrons. When I check xenon, it has 2, 4, 6, 8, 10, 12 valence electrons. This is an example of an expanded octet, so it's done. Sometimes you can look at a formula and see that it's going to be an expanded octet. The central atom is going to have like 5 or 6 things on it. Other times, like xenon tetrafluoride, you have to go through all of the steps to then see that it's going to have an expanded octet. So I have 14 non-bonding pairs and 4 bonding pairs. 14 plus 4 gives me 18 times 2 gives me 36. That's how many valence electrons I wanted in the Lewis structure. I can tell that the Lewis structure for this molecule is going to end up being an exception with the central atom having an expanded octet. Because what I see in the formula is we have phosphorus and 5 fluorines bonded to it. So phosphorus is going to have an expanded octet with 10 valence electrons total. But to draw the Lewis structure, I'm going to set up the inventory. There's 1 phosphorus and 5 fluorines. Each phosphorus contributes 5 valence electrons. Each fluorine contributes 7. I'm multiplying across and adding to get a total of 40. Phosphorus is placed in the center. I put the 5 fluorines around it. Each fluorine is connected then to phosphorus using a single bond. That uses up 10 electrons total to give me 30 left over. Now I'm going to go through and fill the shells of the outer elements. As I fill each shell, I'm going to subtract from the total. So I fill that first fluorine. I now have 24 valence electrons left over. I fill the next one and I have 18. I fill the next one, I have 12 left over. I fill this next one, I have 6 left over. I fill that final one, and now I've reached 0. When I check the central atom, it has 2, 4, 6, 8, 10 valence electrons. It's an expanded octet, so it's done. There's 15 non-bonding pairs and 5 bonding pairs. 15 plus 5 gives me 20, times 2 gives me 40. That's how many valence electrons I wanted in the structure. To draw the Lewis structure for selenium tetrafluoride, I'm first going to start off by doing the inventory. There's 1 selenium, there's 4 fluorines. Each selenium contributes 6 valence electrons, whereas each fluorine contributes 7. I'm multiplying across and adding to get a total of 34. Selenium is placed as the central atom, 4 fluorines around it. Each fluorine is connected to selenium using a single bond. That uses up 8 valence electrons, so now I have 26 left over at this point. I'm going to start to fill the shells of the outer elements, and as I'm doing that, I'm keeping track of how many electrons I'm using up. When I finally reach that last fluorine and fill its shell, I now have 2 electrons left over. What I'm going to do is I'm going to place those 2 remaining electrons as a non-bonding pair on that central atom, and now I've reached 0 electrons left over at this point. When I check the central atom, it has 2, 4, 6, 8, 10 valence electrons. It's an expanded octet, therefore it's done. So there's 13 non-bonding pairs and 4 bonding pairs. 13 plus 4 gives me 17, times 2 gives me 34 valence electrons. That's the number that I wanted in the structure. Before I even draw the Lewis structure, I know that this is going to be one that has a central atom that is an exception. Boron wants to have 6 valence electrons in order to be stable. So when I go through to draw the Lewis structure, I'm going to create the inventory. There's 1 boron and 3 hydrogens. Each boron contributes 3 valence electrons, whereas each hydrogen is going to contribute 1. I multiply across and add to get a total of 6. Boron is the central atom. I place the 3 hydrogens around it. I'm connecting each hydrogen to boron using a single covalent bond. That uses up all of my valence electrons. When I check that central atom boron, it has 6 valence electrons. But what I have to recognize is that it's an exception. Boron wants 6 valence electrons, so it's happy and stable. There's nothing else that I need to do. So there's 0 non-bonding pairs, there's 3 bonding pairs. 0 plus 3 gives me 3, times 2 gives me 6. That is the number of valence electrons I wanted in the structure.